die immer jetzt aber Null
Dann herzlich willkommen zur vierten Veranstaltung. Sorry, it's English. Welcome. The fourth lecture on Introduction of Quantum Field Theory. We were heavily creating particles yesterday. So we're coming up with a formalism that allows us to describe not only many particles, but also situations where we create particles and lose particles, up to having no particle at all. We started first by looking at one particle, so solved the normal quantum mechanics for a single particle and found some energy eigenstates. And I'll write them down. So we are talking about 0.2. Yes, 2.2. The many particle quantum mechanics. Particle quantum mechanics continued, right? So there's stuff if you write, and then somewhere you'll see a picture that is really big. It's 2 boards big. So down here, I'll have my single particle states. We have a ground state, size 0, and you're allowed to, but not forced to, think of this as the ground state of the harmonic oscillator. It's something, could be later, it will be something else possibly, maybe the particle in the box or so. And then we have an excited state, psi 1, and then we have psi 2, psi 3, psi 4, psi 5, I don't know. Goes up to infinity, really. And I label them by the number k. So k is 0, 1, 2, 3, 4, 5, 6 here. And if you have just one particle, I have a box where I can put my particle. Yesterday, this picture was vertical, and this is the energy scale, so you could see how the energy grows with this quantum number. Now I lay this flat, so energy goes this way, potentially wrong state, and so on. And if I have one particle, I put one dot in these boxes. Let me erase this in a minute. So here, this would mean I have a system where the particle is in this state. And now, however, I want to have more than one particle. So I'm going to go into the second dimension here and make boxes in this direction. Maybe I was too generous. I don't need that much. I left some space, so never mind. Now, what does that mean? This means how many particles do I want to have in my multi-particle system in this state? And I allow for no particle in that state. So this is actually a 0. A second ago, this was one particle here. So this has to go up now. This thing means now one particle, this number 1 in this state. And if it was here, then it wouldn't be a particle in this thing. So if I only want one particle, then I don't want any here, any there, any there, any there. So all down here. This picture is a state in my many particle system. It contains how many particles? One. You see this here because it's just one. You just count 0 plus 0 plus 1 exactly. And you even know it is this one particle is in the single particle state number 2. That's how it works. And if I put this here, then I don't have any particle. This is my vacuum. So this picture is this vacuum state. And now, I don't know. So I copy the same that I have here. It can't. No, it can't be those. Nothing there, nothing there. Number 3, 2, 3. Nothing there. 4, 1. Now, how many particles is this? Oh, that was fast. Probably 2. And how are we going to write this? Because I can't draw this picture every time. You have something that's called occupation number representation. So it's a way of writing the state in a convenient way, and it is just these numbers for all the different Ks. So it really, let's give this number a name. This axis here is the occupation number. And really, we have one occupation number for each single particle state. So it's an NK. K tells me which state do you want to know, and then how many particles are in there? Oh, 3. So N 3 is equal. N3 happens to be 3. So I write the state as just the set of all these NKs. I mean, N1, this is just short. N1, comma, N2, comma, N3, comma, all of them. Infinite. I don't know what's better to have an infinite list to write or this picture. So for example, this state here, example, this example there would be 1, comma, nothing, comma, nothing, 3, 0, 4. Oh, this isn't going to work. You can only have one dot per column because it has to decide where it goes. So it's a 4. You can have many in a row. You can have all down here if you want, but you can only have one in each column. 4, 1, 0, 0, 0. Right. And since it's infinite, at some point you don't have particles anymore, or I don't know, even the formula or. In the old notation, this is psi 1. This is psi. Do you want to do this? So how does this work? Before we had the psi's, how many psi's do I have to have? What indices are they? Let's see if this makes any sense here. So it is a tensor product of these single particle states, but how exactly this example? Yes.
Psi 1.
Do I have psi 1? Because I know
Zero,
psi 1, and I
zero,
thought
zero,
1, 1, of course.
Zero.
Exactly, it's this 0.
Yeah.
Because we have one of this, so we need one in a ground state.
And then 3 psi 3s.
Then we need This is the three, which has how many, and then of what of 0, 1, 2, 3. So that happens to be an amazing choice I made there. This three is not this three. This three is that you have three of them. Now let's see if this is a little any better. So we have four of 0, 1, 2, 3, 4, 5 excited. So we have to have 5, 5, 5, 5. And then we have 1, 6. That's it. Here it's a finite list because you figure out there was 9 particles, 1, 2, 3, 4, 5, 6, 7, 8, 9 particles, and these are the states. Here we have this infinite list. So, but somehow this is it's different. I don't want to say it's better. It is better, but it is longer existing. And then you can say, oh, I want the bosons, so I put a little plus and a plus to symmetrize it. And you can symmetrize it, even though there are more. You can't anti-symmetrize it. This state wouldn't be allowed fermionic state. How would a fermionic state look like? What's allowed in someone else? Yes,
Can I ask?
yes, yes. Anytime.
It's not very clear to me why the occupation number statement. Isn't that already a class state?
Yes, kind of.
Because otherwise it wouldn't be a unique state in a way.
I can have a. You have to. So if it was, let's do an example. If I have, I need 2 particles at least. So let's do. We can either do 0. Or we can do 1, 1. Or this other one somewhere else. So that would be for the 2 particles. I want to give a simple example. And now this is psi 0 tensor by 0. And then it's short like this. And here we have psi 0, psi 1. And now it's indistinguishable, so I have to symmetrize and anti-symmetrize this thing. So I really have to put plus or minus, and that means well, it's the same. That's the same. So it's just that. It's just psi 0, and the other with the symmetry is that. Or here I have psi 0, psi 1, plus or minus psi 1, psi 0, 1 over square root 2. So this is like the same single particle states occupied, but I can do this or this. Here the lower is 0. So I have to kind of label it here as well.
No, I don't. I mean, okay, I see the
Isn't it
point.
the combination of both types? Oh, it's not even.
Well, it's really what I want. If I write just this, then I'm thinking in this. Then I'm thinking distinguishable particles. Particle number 1, which I can distinguish from particle number 2, is in the ground state, and the other one is the first excited state, and I know who's who. And that's an element in this Hilbert space without anything. And then I have a similar notation. Which is plus or minus. It's a different state from this thing, but it is built from these, one in this order and one in the other order, with the plus minus. So in this occupation number representation, I define like that, and it can still go boson or fermion. But again, I really only want the concept and how this picture now really is a quantum field theory rather than how is the connection. symmetrization and decimalization, okay, fine, but that's a detail. I only want to discuss the bosons for now anyway. The question was, and you wanted to give the answer, how would qualitatively, even further back, a fermionic state look like in this picture?
There wouldn't be any there wouldn't be any numbers above one.
Exactly, so it can only have this band, where you can choose each single particle state to be there or not. Two is just not allowed because of the indistinguishation example. Now, the way to move in here, to create the particles, we kind of started it. We have these oscillators, so I give the example for the simple harmonic oscillator for the one particle case to remind you of this oscillator business. So here we had something that brought us to the next state. And so on, and we can also go back to the alpha. Oh, I wanted to enhance. Now we're sort of copying this, mimicking this for the way up. So I will have a operator that brings us from there to there. It's called a dagger when it goes up, and it's called a without the dagger when we go down. And if it acts on k equals 0, then it gets a 0 there, because here will be a different one. This is a dagger 1, and this is a 1. And so on. One more. A dagger 2, a 2. And here, this is the same. A 0. And a 0 back. A 1 dagger. A 1. I'm just saying they exist. These are operators certainly that act in this Fock space. So we have an operator that works in this thing. That's basically the state, this space. All of these possible states and superpositions is this and really I'm doing the bosons. And then I have an A, K, dagger that I want to be able to act on these states. So I'll take a basis state in this occupation number representation. So there's stuff here, and then at some position K, let's say we start with 0, N0 is the first, and then there's NK goes on, and this is supposed to be one more NK, one more at the K position. So N0, NK plus 1, and then what we had. If you remember the normalization we had yesterday, we'll just copy the same thing. So we have NK plus 1. That was what the ladder operator said. The names here, if you want to be precise, this way it's the raising operator because it raises your energy. This is the lowering, and together they are ladder operators. And this way, it's a creation operator, and this way, it's an annihilation operator because you create a particle and you annihilate a particle. But since it's basically the same thing, the language is misused. People say it's a creation in this way too, and this maybe it's a raising, so it's get messed up. But it's two different things. One increases the single particle state, and this adding a particle or taking one away. So this is taking this is adding one. And the case does this for makes sense. I can claim that the Hermitian conjugate is the lowering because we know it from here, but I don't think that's safe to say that. we don't have an expression of these in terms of x's and p's and know what their mutation relation is and all. We don't know anything. I just said we want to go up, right? This came out of thin air. So I want to justify that the Hermitian conjugate of this is really the one that brings you back down. It does. You don't need any x's and p's. We can take this equation and take the adjoint. So here, this equation adjoint. Then the state flips nk. This thing gets the dagger taken away, and then we have equal, that's real, nk plus 1, n0, nk plus 1, and that's it. And now I will multiply this with the state from the right, because I want to have an equation where this A acts on something like this. So I really want to multiply this equation, different color. Now the operation, that's what I'm doing. To the equation is in blue now, in green. So I want to multiply this from the right with exactly this. So n0, nk, but that's not a good thing because you have this already on the left. So I give the numbers on the left a prime. Because the equation doesn't get not wrong if I have prime. So the numbers, the occupation numbers are just prime. They're different letters for the same. This holds for any n. This holds for any n primes, nothing wrong. So now I can multiply without conflicting this. I could have multiplied before, but then it's more special. Now I have any combination of n and n primes left and right. So I multiply it now. Then I have n0 prime, nk prime, a, k, n0, nk, that is equal to square root nk prime plus 1, n0 prime, nk prime plus 1, n0, nk. Here I don't know what's going to happen. In fact, I want to figure out what is happening here. This is just the scalar product. And so it's like pairwise. This scalar product with these and all the dots, and then these together and all the other dots. So, and then they're also normal. So I get delta function. This is equal to square root nk prime plus 1 delta. Now the n0 prime has to be equal to the n0 for anything to be left. If that doesn't, they're not the same at 0. They are not the same 0. And here something interesting happens. So nk prime plus 1 needs to be nk, which means this needs to be 1 larger than that, or this needs to be 1 less than that. In fact, I can write sorry, yes, times all the others. Now I can write nk prime plus 1 is equal to nk, otherwise there won't be anything. So I can change this to nk, no prime, no plus 1. They're the same. They have to be the same, otherwise it's 0. So yeah, so they are the same if it's non-zero, like this. And then I have, to do it quick. The quick version is the primes, take away 1 here too, and take a 1 there as well. N0, nk minus 1, Now, this will give me the same delta functions because this is the same as delta nk prime nk minus one. Roughly, there's a boundary case, but let's figure out whether it's roughly right. This says this says nk needs to be nk prime plus one. And now I bring the minus one on the other side, so nk minus one is equal to nk prime, and that's what this thing claims. That's the same thing. And then I put this back into the scalar, and this is the scalar product, nk prime with nk minus one, and that's part of it. It doesn't work if this is zero, because if this is zero, this has to be minus one. Well, it can never be minus one because they have to be positive or zero. So all of this works if nk is larger or equal to one. So larger than one, larger than zero, I guess. Same thing. Let's say larger than zero. Or equals 1, 2, 3, 4. And now this equation read from here to here holds for all primes. And since this is the same thing on the left-hand side, and it's a basis, it means that the thing that it multiplies is the same. So we can conclude that AK has 0 nk is equal to what? This square root nk n0 nk minus 1. So that wanted nk to be larger than 0. And what happens if it is 0? If it is 0, well, then we cannot satisfy this. And then the scalar product is 0, and we don't get anything. The upshot is this follows from here. So this is exactly what we had for the simple harmonic oscillator and the alphas. You could even include the bottom case up here if you wanted, because if nk is 0, and since there's a screw at nk, that makes it 0. If you're comfortable with writing a state that doesn't exist, 0 times a state that doesn't exist. So it really doesn't make any sense to have a minus 1 here. If that's there, then there's a minus 1. You don't really want that state, but it's multiplied by 0. This is the proper way, writing 2 lines, but it really is the same. Yes?
I have a question in general about creation and annihilation operators, like about the intuition. Why, if we just apply like a creation and then annihilation, why don't we usually just get 0? Just get back to our original state?
Oh, this is like you planned this question. I think I didn't know where to put this. I wanted to remark it again. That's exactly the opportunity to go back to this. So you were saying we have a state. Let's do the simple case, right? It's going to be the same here, it's just longer. So we have some state with some number, and then we have an what did you want first? Either way, right? Let's go down first. Let's go down first and then go up. In the other notation, it would be nk And then we have an A, K, A, dagger, K. Same thing, right? Here it raises and lowers, first lowers and raises the occupation number. Here it the energy. So what does this do? And your question is why is this not equal to psi k, or is it? Is this
I mean, also like, it looks like it's not, and then it's like, okay, like from my intuition, why is it not?
right? Let's do and see what it is. It is alpha dagger, and then we get from lowering. Let's say this can be lowered. Then we get this factor, it's square root k, and then we are at k minus 1. And so this square root k is where it is. And the basing operator here gets the square root, the number, level number plus 1. So one more than the number of the state, which is funny because this is k minus 1. So we have to have a square root of k minus 1, which is this, plus 1, which is that one from there, and then raise it to k. All of this mess is just k. So you get k psi k. So you do get what you got, but with that k, do you like it? I don't know. Do you like that k?
Not really.
Oh, yes, you do, because then this operator you call the excitation number operator, right? You have a state and you act with this combination, and the eigenvalue, if it's an eigenvalue, eigenstate of this operator, then the eigenvalue is the excitation number. So you can test how high is the energy. In fact, your Hamiltonian for the simple harmonic oscillator was this thing. So it's either this, in these funny both orientations, or if you flip one around, then so I can change this. Then I have twice this object, but I have from the commutator 1. So if I have 2 here and 1 there, I can cancel the 2. So this is equal to h bar omega alpha dagger alpha plus the 1/2. There was 1. This is Hamiltonian, and now this is your excitation number operator. So if you act on an energy eigenstate, this is just the k. So that's why the spectrum E k is with this prefactor just the k plus 1/2. So your Hamiltonian just counts this k, the excitation number. And the reason why I like talking about this now is now I can say this was so beautiful, but now I can say this combination deserves a name. Which name? Or which letter? Oh, I erased it. Here, this number, it spits out this number, right? This is the nk. So you have an operator. When acting on this collection of dots, gives you the number of the k, one particle state, the occupation nk. If you didn't like, for some reasons you don't want the k, you can of course define other operators. You can define a new operator, I don't know, and which is then 1 over k. No, that doesn't work, because you have the k there. You need to, well, I guess it's cute. And you can't have this because they raise and lower, right?
Can't you just like change the alphas themselves, the ones that go up, and well, I guess then you use.
But I can normalize them in a different way, but it can't. So these can depend on the state they act on. I mean, you can't choose different operators for every state they act on, and then it's not good for any operator. Yeah, that's how I think.
So in general, if we apply these operators, we always kind of lose normalization, and we would have to like we always get a state that's not normalized if we just apply these randomly to some state.
Right, and that losing sounds very negative, but it is a good thing because this is why they are number operators and they count stuff. So because this number alpha dagger alpha, the number operator with alpha dagger, this is alpha dagger. So this one will be counted. If you raise it to the k, you'll just get a k here. Because this acts on every factor. That's the right thing, yes.
Yeah, and if you, it's not very problematic that they don't think, because like those aren't real observables anyway, right? They are not
Yeah, no.
Hermitian, those are, so in some sense, they are mathematical constructs anyway.
Yeah,
So it
that's
doesn't
what
really matter that they don't produce what we would intuitively think, because they aren't physical quantities anyway. It's just a construct we use in order to get to the occupation number.
absolutely, yeah. This factor isn't the problem anyway. Isn't the problem at all.
Yeah.
If we want another operator, then we do, but this is one I like that because it counts things.
Yeah, this one is Hermitian, this one is real, right? Yeah.
Because if you dagger it, then
Yes.
you have to dagger each of them, but also reverse the order, so it's perfect. And then I define another one, n, which is the sum over all k's, nk, and then this tells me how many bit fibers do I have in total. What else do we want to know? Now we want to know. I'll be that fast. That was. Well, let's start the operator business. So, as you said, this is very artificial. It's something that I just wrote down. Let's connect this to something more other observables, maybe Hamiltonian, maybe some time evolution, so that this thing actually does something. So now we're talking about more general operators on this set, and then define a Hamiltonian. And in chapter 2 and 3, operators. And now comes operator value here. Of course, I can invent now anything that acts on the space, but what I want is to generalize something that worked for the one particles to the many. So let's first look at an operator that acts on the one particle Hilbert space. So this H1, what is a good operator here? It is something that I call A is generic for an operator, or that shows it is one, and one is something that acts on these one particles, and now I can have a psi k. And since we're only talking about linear operators, the result will be a linear combination of these states. So I write this as that. Sum over all L, and then this one. So basically, if you think of this as a matrix, then these are the matrix elements. This is the column. You can write this as if K is psi 2, you can write as 0, 0, 1, 0, 0, and stuff. Matrix representation, here columns, and this operator in this matrix, this representation will be a matrix, and these are the matrix elements. And why do I do this backwards? Why is this to the right, not on the left? Because if I multiply this equation with a psi, say L prime from the left, then I get psi L prime A 1 psi K sum over L, and then psi L prime psi L A L K 1. And this thing is delta L prime L. So in the sum over L, I only get something non-zero if the L is L prime. So the whole long sum becomes just L prime, that one. And now it looks nice. The one that is on the left is the one, the left index. And the one on the right is the right index. And now just the prime is annoying, but I have to go through it. We could change it, but all right. So now I have this operator which acts in this space, and it has these coefficients, these matrix elements. How can I now define an operator in this space? It's A hat without a 1, which has a nice action, a well-defined action on everything, on the whole, and reproduces this action if the state happens to be just n equals 1 state. And the answer is, you take this basically, A, K, then your A1 KL, AL, sum over KL. So this is now the definition we make for an operator on the entire Fock space from an operator acting on, who's actually known as one particle. And so first we figure out what these A1s are, we stick them in here, multiply the raising and or the creation and annihilation operators left and right. Let's just see that that actually works. Let's see that this on the single particle states produces what we want. So now this thing on psi k, and it should be the first line. That's equal to sum over k, be careful, so lm al a1 lm al, and that is psi k. This thing is created from yeah, it's basically, where is it? Like k, say k is 4. This no, there's no. It's this thing. It's created from the vacuum using the A thing. So this is proportional to A dagger K from the so-called vacuum. And this state, this is short for your favorite state, 0, 0, 0, 0, 0, 0, just nothing. Here's a place where we need it. I'm not saying we live in this state, I'm just, that's a good one with someone there, and it's created from it. So in these occasions you use it, but otherwise. Okay, now I use the commutation relation of the two. Why? Because otherwise I can't do anything right, really. All I know is that this guy annihilates 0, so I want to bring it to the other side. So that is equal to A dagger K A L. Turn it around. then add a one. Oh. Oh, we haven't done that. Maybe this is why it was so fast. You have to show. Sorry, this needs to go before this discussion. Can show that A, K, and A dagger L, we know how they act individually, then we form the commutator, and it makes sense that you get a one, they're the same, and zero if they aren't. If without any computation, you'll trust me because we have done the computation. Oh no, it was an exercise. In this case, and since we have the same factors of k and square root of k, this has to come out here as well. And if they're both undaggered, A, K, A, L, then you always get zero. And if you go complex Hermitian conjugate with this equation, then this can't suddenly give something in there, so also zero. So having this, I can actually switch the order. And if the K and L is the same, I get one. If they're not the same, I don't get anything. So I have my delta KL here. Now, this annihilates the state. So the first term doesn't result in anything. Therefore, I have sum LM AL dagger A1 LM. And these are gone, right? These are gone, right? Just with delta KL and then like zero with some proportionality constant. What's the constant? The constant is 1 over. It's just this. You also homework. You figure out what the normalization is, right? If well, didn't we say if A dagger K on NK, this is equal to square root NK plus 1 NK plus 1. And now I'm using this with all zeros, so this is just the 1. So it's not just proportional, this is equal. This is equal to this. Now summing over L explicitly sets the L equals K. So I have sum.
Excuse me,
Yes, here.
sorry, could it be that in the sum on the right-hand side, one of the L's on the annihilation operator should be an M?
Could be an M. Thank you. Zoom land. We are sleeping here. It's this. That it was an L there, but I had to rename it because there was an extra K. Thank you. Exactly. Now this is all different. This must be an M. And this is an M, and then this is an M. To be honest, it looked suspicious because usually you only have two of the same kind, but I thought, oh, well, all right, it looks much better. Now, summing over what? We can sum over both. No, we can't sum over both. We can sum over M. K is the external one. We can sum over M because we know what this is. So it sets the M equals to K. So we have A L. Another A L K and 0. And these two together is a psi L. So this is equal to psi L, A, one LK, sum over L, and that's what. Thank you, yeah, that's what it was supposed to be. Yes.
When we apply the AM to the zero vector, then we get like a zero that's different from the zero vector, or what do we?
Zero that's different from the zero vector, where's the vector? So you're talking about the state here?
Yeah, like
This is the vacuum, and if you activate what?
with the AM.
Oh, a zero,
Yeah.
good point. What's all this nonsense? So many zeros. Oh, I wish I hadn't done this. What is psi zero? In comparison to this? Well, we know that this thing is 0, 0, 0, 0, 0. There's no particle at all in no state. This is how many particles? Last.
Like
So it's one. In which state? Oh, in the ground state. So this
No,
is equal to.
No, what happens if you lower the zero vector, like the vacuum?
Lower this.
Yeah.
You can't lower it because then that's what we used here. The lowering on this is zero.
Maybe I just misread the equation. I mean, then it's whatever.
No, wait, let's figure this out. The bracket is this.
Yeah.
Then I took these two,
Yeah. And you apply these onto the
Turn.
zero, right?
and then,
The vacuum.
right, and then there's a zero waiting, and this kills this.
Okay, and what does kill in this case mean? That it's
Kill is the wrong word, like, zero.
okay, so there's a zero that's different. That's
Oh, of course, yes. Now I understand. There's lots of possible confusions. For example, this, like, why is the ground state not the ground? So this is now called the vacuum, but some people call it also the ground state because it's annihilated by all the other things. This thing you would call the ground state in this one particle business, but sometimes also this is called the vacuum. If you no, misuse language. So these can be confused. Also, this looks pretty much like psi 0, psi 0, psi 0, psi 0, huh? But this is also something different. Well, this has to go on this side. Psi 0, psi 0, psi 0. So this is an infinite particle state, and that would be this. This is the occupational number representation of this, and you have infinitely many in this state, and that would be equivalent to writing this thing. I could also write it there because it's equal, but it makes more sense. This is. Now you were confusing or asking, is this the same? No, but it isn't, because you have your Hilbert space with all these arrows, and there's one arrow that is this thing, and the zero is a number. It really is a state.
Yeah.
It represents a state in which the system can be in. Although it has a zero, like there's really nothing, but it is still a good state.
so like
So that's
the zero without the brackets is like a part of our vector space, but it's not a normalizable state. Okay, that's
Yeah, you can multiply everything.
Yeah.
With zero and then. All right, so now in your homework, you'll try out what this more general operator A does on two particle states. On one, it does what it's supposed to be, so we can construct it that way, and on two, so if you have psi n, psi n, mn, then this is going to be A1 operator on psi m and then psi n plus psi m a acting on psi n. So this thing that we constructed and define in this way acts as the one particle operator in the one particle sector, and in the two particle sector, it acts on each of the constituent particles. We have three, does the same, it's like a product rule. And this is exercise. And the computation is just like this, except for you have two states and the two creation operators, you have to compute twice, and then you get two terms. Now, I want to write the operator here in a coordinate representation. So if you have a coordinate, if I have my operator A, I can have these matrix elements here in the energy basis, and now I want to define this in the coordinate basis, so I just take the expectation elements. Right, I'll take the coordinate. And well, I guess I want still the one. It's not explicit, but if I give you an A, then you can figure out this thing. So if you have this, how does this equation look like in the coordinate basis? This is going to be the core. Now the transition to quantum field theory or field theory happens. Now watch. Because we didn't have x's and y's, now we're going to have x's and these are fields. Just functions, but anyway. A is defined as KL, AK, dagger, A1, AL, AL. And we convinced ourselves that this makes sense. Now I want to use this. So I'm going to throw in, this is equal to KL, A, K, psi K, A operator, psi L, AL, nothing happened, just what this was. Now I'm going to transform this one to this one by adding here, insert a identity operator, which is dy, say, y, because my position states are complete. And here I insert an identity, which is dx, x, x. Why do I do this? Because then these two, okay. Now I have some k and L and integral the x, dy, a dagger k, psi k, x, x, a 1, y, y, psi L, a L. Following, everybody? Now, this was by definition, there's the function xy, the matrix element in the coordinate basis. These are just the weight functions. Here's what's happening. We had the state, and if we project it on the coordinate system, so this is the wave function, psi L of y. And if this is the harmonic oscillator, then this will be the Herbig polynomials, or if there's something else, then it will be something else. Like if this is your box, then it will be sines, whatever you get. It is the wave function of the states of this single particle system underlying the whole construction. And here it's the inverse, the reverse, so it's the complex conjugate of this. This is psi, the complex conjugate wave function. And now here, A, same A is integral dx dy, and I'm going to collect the sums with where the indices are. There's a k. So I'm going to write sum k, a psi star k, x, a k, dagger. Then I have the a one, x and y, and then I have stuff with L, and then some X, A, L, this. So the K's are only here, the L's are only there, and then we have an X on this side, and Y on this, oopsie. Very good. And then we integrate. When you look at this, you want to give this thing a name. So definition, the psi, this thing, the sum over L, psi L, X, let's be generic. Yeah, let's K with my letter, A, K. This thing, we'll just call this the operator, which depends on X. It's an operator because there's an operator, it's a function because there's an X. So what we do is we take all the wave functions, the entire spectrum of this one particle system, and then these creation or annihilation operators that we introduce to move up and create more particles. These we put together. The wave function of the one particle system with the particle creators and annihilators and sum. And that is an operator depending on X. And the dagger of this works beautifully is the psi complex conjugate and then the A dagger. So it's that object over there. So with this definition, the A can be written as integral dx dy psi dagger x A x and y for the one particle psi of y. Ooh, beautiful. Or maybe even here, maybe in red. You know, this is, it pops up as a definition, right? We put this together and then we deal with fields. What's yeah. Here's really where we were. Why is this talking? It just pushes and see what we get. I want to construct a Hamiltonian. I'm going to look at a potential. So example. So potential energy operator. So we will eventually get the E hat. We start from this function. That's the classical version. Then we go to the one particle operator. This is the function value where you replace X by its operator, so you have this one particle potential energy A. And now we're going to use, I guess, the this representation here down there. So we want to compute V1 of X and Y, which is defined as X V and X hat Y, right? It was here, and it is still kind of clear. This thing that I'm supposed to insert there is the matrix element of my single particle operator in the coordinate basis. And what does this do? These states, the position states are, do you want to say that? Yellow shirt. What's going to happen here? Oh, well, let's say, what is this? The position operator acting on a position eigenstate. It's not going to get more convenient than that.
Just like y.
It's just like y. It's y and y because this really labels the eigenvalue of the state under its operator, right? Does that make sense? Like with the end. Well, the position basis really means that it's an eigenvalue. So if I can, oopsie, many hats. There's no hat. This is not the operator. This is the operator because the x is an operator. So this is the function. I can Taylor expand the function. Now it's not. So if I Taylor expand this, then it just powers of it. Every single power of the x hat will be a y. So I have the same Taylor expansion of this function in terms of y. So this is really x y p of y. But now it's just a function. I take it out. So I have v of y, and then I have oopsie, x and y. And what is this? They are pseudo orthonormalized. They're orthogonal in their delta function normalized. So this is delta x minus y. That's pretty. And now my v operator, the one that we were looking for, the operator acts on the multi-particle Hilbert space, is the integral over dx dy. Then with these beautiful fields coming from the left and right, psi y. Now we insert this dx dy psi dagger x v of y delta x minus y psi of y. What do you want to do now? What do you want to do now? Simplify things.
We want to use the delta function to like replace one of x or y to.
Which one do we want to?
I would like to keep x.
You want to keep x too, so we're on. So we're gonna get rid of x, so put x is there. So then we have integral dx psi hat x v of x psi of x. Boom. Squeezed in there is the energy, the potential energy operator in our multi-particle universe. This v is just a function. You can put this in front, in the back. It's not outside the integral, but this doesn't have to be in the middle. These things don't commute because the a's don't, but the v can go anywhere. So wonderful, we have that. Now let's go to the kinetic energy operator, also known as the Hamiltonian. This is now real fun. Yeah, so we need, so the kinetic one is just this H0. I write it 0 to say this is like the free Hamiltonian. It depends on P, it's P squared over 2n. So our one particle operator for just the kinetic term is P hat squared over 2m. And then we have to take the expectation. So we need H 1. Yeah, well. If of X and Y, it is the X and now the H 1, 0, this is 0, Y. So that's what it is. No, that's what it is. And now we have 1 over 2m x p hat squared, where's gone? P hat squared y. How does p act on x? We know what x did to the position, but what does the momentum do? Yes.
Would you either do the Fourier transformation or just del X?
Well, I don't like the, I would, the short way, the shortcut really is to do the partial derivatives here, but it can't act on states. It can only act on the wave function. So let's do it properly with the same result. We insert here another one, but go to momentum space. That was your proposal. I will keep it P. That's why I really want hats everywhere where there's an operator. This P isn't that P. It looks the same. It looks like I forgot P, right? Or something. I could write Q to make it obvious, but this is not the same. It's like this Y here wasn't an X that has his, which one? Yeah, anyway. Okay. That's so I insert his integration variable P, and then 1 over 2m x or integral P x P hat squared on P and y. You know why it's so I was going to say silly, because what is this? What is P hat squared on P? It's just now I can basically forget about the hat, right? But it's non-trivial what's happening here. It only worked in momentum basis. You couldn't just go like, oh, this is Weiss. And these things are now the basically plane waves. That is e to the usually I p y over h bar, except for this is not the other way around. This is the complex conjugate, so there's a minus sign, and then they're normalized. If I want to use the normalization of the delta function, I have to have a 2 pi h bar. That's what this is. Now, H01 x y is 1 over 2m integral dx p, no dx. And the p squared can go into the front. This x with this p is e to the I p x over h bar with the square root. And then we have this thing, e to the minus I p y over h bar divided by 2 I h bar. This is what we have. I would like to perform the p integration. If there wasn't the p squared, I could do it because I know that the integral of bu e to the I u v is equal to 2 pi delta V, right? If it's exponential, then in integrating over it, you get the delta function of the other part without the I. You could even have a minus under the math. This is symmetric. But this is disturbing, and what people do is they replace this. Use p squared e to the I p x over h bar. Replace this by this thing. Because the derivative with respect to down, you do it twice, pull down two p's, correct for the other crap that with it, and then you have this. This is how the momentum operator comes about in the first place. So then we have 1 over 2m. This doesn't depend on my integral. So this thing acting on everything. Then I have an integral over p e to the I p x minus y over h bar 2 pi h bar. And depending on how much seconds I have, this is delta x minus y. Had a more, it would be a few more steps. But maybe you accept this for now because it's another funny punchline. So the answer is, it is 1 over 2m minus I h bar dx squared on the delta function. The worst thing ever, right? The kinetic energy the matrix element for the kinetic energy operator is this. On the other hand, it's just p squared over 2m. But you can see that it's right. It's strange. Now I am going to insert this somewhere. My h hat in the multi-particle theory is integral dx dy and then psi hat x h 1 xy psi y hat. And now this thing comes in here. And then it's equal to integral dx dy psi x minus I. This is also annoying. This is h bar squared, a minus sign, 2m. And now it's just a derivative of delta x minus y psi y. And now we want to get rid of the delta function, use the delta function, but before doing that, we have to get rid of this, or maybe it's let's do the partial integration twice, so the sign doesn't change. You get the derivative here, so it's minus h bar squared 2m integral dx dy dx squared psi hat dagger x delta x minus y psi hat y. Now we use it, which really sets this to x only. And then we have minus h bar squared 2m integral dx squared psi x psi x. And just for good measure, we integrate once more by parts to get both of them, the derivative. Then we have the minus sign. So it's h bar squared over 2m integral dx psi dx. So we can even do it. Dx psi x and dx psi x. There is your kinetic energy operator in the multi-particle theory. It really just gives you the if this acts now in a state, these are operators, right? It just finds the total kinetic energy. Just no matter how many particles you have, and we have to add the two. So, for total Hamiltonian. Write something else there. H is then this and this. And so then we have integral dx h bar squared to m dx psi dagger dx psi plus psi dagger v. You know, I've been a bit sloppy here. You have to make it clear, yes. With my argument of x, obviously. So there it is. The kinetic part, potential part, and it acts on one particle states as you would expect, and it is the generalization for the multi-particle states. But it doesn't. There's nothing truly two-particle or n-particle in there. It just treats every particle separately. I gave the example. How does this act on two particles? Just here and there. It asks the first particle, what's your kinetic energy, what's your potential energy, and then adds them all up. There's nothing really interacting there. The particles are independent. So it's a total Hamiltonian operator of non-interacting particles. So it is an undetermined number of particles, could be many more than that, but this is the operator for non-interacting. What's this what's this potential? What's this potential in non-interacting, eh? What's the V doing there? Exactly. This is the sort of external potential that every particle that's there feels. So you have whatever you have. You're not going to run an oscillator and they all sit there. What we really want now is to go truly to interactions. 6 minutes. And
So question,
every time, anytime.
what happened when the differential and the delta function moved to the y up there? I don't know.
What happened when the differential moved to the here?
Yeah.
This is integration by parts.
I guess.
And then you say, oopsie, isn't there a surface term? Like total derivative of everything? And then the answer is yes, but you have an integral over, well, it evaluates your wave function at infinity, and let's just hope that's 0. So if your world is totally flat, everything free, then it won't be. Your particles can escape to infinity and beyond and anywhere, and then all hell breaks loose. But if you add a little money or something falling there, then your wave function falls off and you're safe. This is the story. You can't make it better than that. It's just honest truth. You neglect the surface. Now I'm just going to quickly add one more line for the interaction. Oh, I need to just say 2 more things. I have to say, first, let's do the interactions. Interactions. I didn't see that page before, and I thought, oh, I have lots of time. I did. Then you can have an operator that now this is for 2-body interaction. Then you start with this a dagger K, a dagger L, and then you have a V, K, L, and N for 2. And then it's an A, M, N. And this thing is equal to psi K psi L V hat for the two particles, and then psi M psi N. So if you have in your one particle, or if you have in your, no, not one particle theory, you have the two particle theory, and then you have an operator that acts on the two particles. It's a linear operator, so it produces again two particles, then you can project it into this, and then you have the matrix elements. It has four indices because you have two there and two there. And then you put this together, and then this will act on the two particle subspace as you have defined it here. It doesn't act at all on the one particle subspace because you have two annihilation operators, which annihilate them, just like the one before. It doesn't act on the vacuum, so this doesn't act on the one particle, only two and higher, and gives you a true interaction in this formalism. And I was going to write down one example. And I want to give the example of a Coulomb. Interaction. Your energy of your two particles at positions x and y is the charge squared over the distance squared. So that's how you start, and this is now the classical thing. Now you make this two particle operator out of it by replacing your two variables now by these operators. So you have your q x hat minus y hat. Now you stick this thing into these states. You go to the coordinate basis. You do all we have done, and I would have written it if I had more than 2 minutes. It's written in the notes, and you end up with the interaction. The integral dx dy psi x psi y q squared x minus y psi x psi y. Now you have a term that you could add to the first line up there. So this is now an interaction between them, between all the particles. So what it really does, if say you have three particles in the system, so you have a state, three things in there, and when you act with this on the state, it acts pairwise. It acts here, and there, and these two, and so you have an interaction between each pair. It's exactly what you want. You have three electrons, and they feel each other, and that's now a two-body interaction in this many body theory. This was just a one-body interaction, basically. Just it was one thing with the environment, and you can go higher if you want to have a true three-body interaction. So you have maybe something where it matters. So your interaction really depends on the condition of all three. I don't have any of this. Not really typical, but you imagine it exists. Really depends on where all three are. Even if you have three planets, it's always like pairs. They all interact like three, but not generically a three-part interaction. Think of maybe you have a spring connecting the three. Very funny. Then it really is a true three-body interaction because it really matters for. Then you get three of them. You have psi, 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 psi. So the number of psi's in your term tells you how many particles are connected by this. This is the three particles, non-reactive particles. This is the two-body interaction. Yeah. do you want one more sentence? You get one more sentence about why is this called second quantization? Because I called the whole chapter like this, from quantum mechanics to quantum field theory on second quantization. We had, I'll make this clearer next Thursday, since you wonder. So first you have the x's and the p's, and you do a quantization to operators, and these act on wave functions. So by going here, you also went to wave functions. But then here we have now hats on wave functions. So now somehow it looks like one quantization, second quantization. That's why people call this the second. This comes after the other. But that's now you'd say, oh, I just write down I start basically here, forget this bit. I start here, I write down a classical field theory where this is just some classical field. It is not the wave function of some quantized theory, it's just something, like Gordon equation or something. And then you quantize exactly once, this step. But this is where the name comes from, and I wanted you to know. Questions? Yes.
The external potential is still classical, is it?
Yes, exactly. Exactly. Very, very, very true. Yeah.
And I also have a second question. So when this was a while back, we showed basically the Fock representation and the state representation are sort of equivalent, right? Occupation number representation and state representation. This is also saying something like it is equivalent that there's a one particle or there's infinitely many unoccupied states and one state is occupied, and one of which you automatically get the idea of the field.
Right.
Right? So
Right.
this is how you go from one
Yes.
state to a field.
Yes.
Okay.
Exactly. Exactly. You empty all those. You open up the empty boxes in this gradient. Wonderful. Okay. Well then, let's all have a good weekend.